Hello, everyone. Today, I will report our team's latest work, named Transformer-Empowered 6G Intelligent Networks, from Massive MIMO Processing to Semantic Communication. The outline will include 6 parts: Introduction, Overview of Deep Learning, Transformer for 6G Intelligent Processing, Challenges and Open Issues, Conclusion, and References. The 6G of wireless cellular networks is expected to connect the cyber and physical worlds, allowing humans to seamlessly interact with a variety of devices in a mixed reality metaverse through connected intelligence. These new and fascinating applications impose challenging requirements and constraints on communication networks, including ultra-high reliability, ultra-low latency, extremely high data rate, substantially high energy and spectral efficiency, ultra-dense connectivity, and a high level of intelligence. Here, we list some requirements for 6G. The 6G should provide seamless wireless coverage by multiple heterogeneous nodes, such as satellite, UAV, terrestrial, and maritime. The 6G should provide much more wider band, such as mmWave and Thertz. The 6G should provide intelligent services by big data and AI. However, the traditional communication design approach is facing increasing challenges in the complex and diversified scenarios in which 6G networks are expected to operate. For example, high-frequency channel environment is more complex and hard to model. The estimation and feedback overhead of high-dimensional channel parameters is unaffordable. Simultaneously satisfying high performance, low complexity, and short running time is difficult for conventional mathematical optimization solutions. In this paper, we introduce the transformer architecture and explore its application in 6G intelligent network design. We present a transformer-based architecture for 6G intelligent processing and study its performance in various wireless communication problems. Classic neural network architectures include multilayer perception, MLP, convolutional neural network, CNN, recurrent neural network, RNN, and stacked autoencoder, SAE. MLP is an artificial neural network that consists of at least 3 layers of fully connected neurons, parameterized by a substantial number of connection weights. To reduce the training complexity, CNNs employ a set of locally connected kernels, rather than fully connected layers, to capture local correlations between different data regions. RNNs constitute another class of DNN architectures that exploit sequential correlations between samples. SAE architecture consists of hierarchically connected multiple autoencoders, which is suitable to apply for communication framework. Although MLP, CNN, RNN, and SAE have been widely utilized in DL-based communication system design with some success, efforts continue to push the boundaries of DL models in practical communication systems. Recently, the evolution of DNN architectures in NLP has led to a prevalent architecture known as the transformer. We argue that the transformer holds a great potential also in the design of intelligent communication systems. As shown in Figure 4, the transformer is a sequence-to-sequence DNN model and consists of an encoder and a decoder module with several encoder-decoder layers of the same architecture. The input and output sequences are converted to vectors of dimension d by embedding and positional encoding layers. Each encoder-decoder layer has the same structure, and is mainly composed of a self-attention sublayer following by a position-wise MLP sublayer, while each decoder also contains a masked attention sublayer before the self-attention sublayer. For building a deep model, a residual connection is employed around each sublayer, followed by a layer normalization module. Massive MIMO is an essential physical layer technology to accommodate the exponential growth of mobile data traffic. Figure 5 illustrates a generic communication system, divided into 2 parts, the MIMO processing part and source and channel coding part. The former includes pilot design, channel estimation, CSI feedback, and hybrid beamforming. The latter is composed of source coding and channel coding. By highlighting the transformer's multimodal fusion and feature representation capabilities, we seek to expand the applicability of the transformer to serve as a general-purpose backbone for these crucial modules. In particular, as illustrated in Figure 5b, we propose a novel 6G intelligent processing architecture employing transformer for both the massive MIMO intelligent processing blocks and the newly emerging semantic communication blocks. Accurate CSI at the base station, BS, is critical for beamforming and signal detection in massive MIMO systems. However, it is challenging to accurately estimate high-dimensional channels with few pilots. By exploiting the sparsity of the channels in the angular and/or delay domains, compressive sensing, CS-based solutions have been proposed to overcome this issue. Nevertheless, since the dimension of the CSI to be estimated is extremely large, the involved matrix inversion operations and the iterative nature of CS-based techniques result in prohibitively high computational complexity and storage requirements. More recently, researchers have resorted to DL techniques to overcome the aforementioned challenges, such as LAMP, MMVLAMP, DNN-based solution, and CNN-based solution. Nevertheless, most existing DL-based channel estimation solutions are based on the MLP and CNN architectures. Here, we propose a novel channel estimator that utilizes the universal and flexible transformer architecture. First, we consider the downlink channel estimation problem in M successive time slots, where the BS is equipped with a UPA with NT antennas, the UE has single antenna, and the number of OFDM subcarriers is K. The received signals in M successive time slots can be expressed as equation 2. Then, by stacking all the subcarriers, the received signal can be written as equation 3, which is a standard signal recovery problem. As illustrated in Figure 6, the proposed transformer-based solution includes a dimensionality reduction network for pilot design and a reconstruction network for channel estimation. We exploit a fully connected linear layer to learn the pilot sequences. More importantly, in our channel estimation module, the encoder part of the transformer is exploited to reconstruct the channel. Unlike local attention in CNN-based solution, self-attention in the transformer can extract long-range correlations between subcarriers and adjust the weight of each subcarrier, so that the global features of the channel matrix can be extracted for enhanced estimation accuracy. To evaluate the performance of the proposed transformer-based solution, the pilot training stage has M equals 24 successive time slots. The BS is equipped with a uniform planar array, UPA, with NT equals 64 antennas. The user equipment, UE, has single antenna. The number of orthogonal frequency division multiplexing, OFDM, subcarriers is K equals 32. We consider a sparse channel scenario with NC equals 6 clusters, NP equals 10 paths per cluster, and an angle spread of delta theta equals 3.75 degree. We generate training, validation, and test data sets of 100,000, 10,000, 5,000 samples, respectively. We consider the NMSE as the performance metric. As shown in Figure 7, the proposed transformer-based estimator significantly outperforms the conventional and other DL-based methods, especially with comparable model sizes. We observe that, during the inference stage, the floating point operations per second (flops) and the runtime per sample of the transformer-based estimator are much lower than those of other DL-based methods. Moreover, we can observe that the performance of the transformer improves with the model size. This demonstrates that the transformer-based method can learn latent features from the data more effectively to achieve better channel estimation accuracy with less pilot overhead. It also provides a flexible trade-off between the model complexity and performance, and the users can choose the operating point based on the underlying resources and application requirements. CSI feedback is essential in frequency division duplex (FDD) systems. However, the large number of antennas result in excessive feedback overhead. Similarly to channel estimation, CS-based techniques can be used to reduce the CSI feedback overhead. However, these techniques cannot fully exploit the channel structure since the channels in real systems are not exactly sparse. Recently, DL-based solutions have achieved impressive results for CSI feedback, such as CSINet, bit-level CSINet, and LSTM-based CSINet. Herein, we present a transformer-based CSI feedback scheme to obtain more efficient quantization and compression performance compared with the prior work. Assuming that channel H is known at the UE, a general representation of the CSI quantization and feedback process can be written as equation 4. As illustrated in Figure 8, we utilize the fully connected linear layer to linearly embed the channel data and use sine and cosine functions of different frequencies to represent the relative positions of the subcarriers. Then, the transformer encoder extracts features from the channel data embedded with the positional information. Next, the features are vectorized, and a fully connected linear layer is used to generate a real-valued compressed code word. The code word is then converted to the feedback bit stream through a quantization layer, which is constructed by uniform scalar quantization. Since the whole network structure corresponds to the compression recovery task, the decoder adopts the same structure as the encoder. We use the same simulation parameters of channel estimation. Figure 9 shows that all three transformer-based CSI feedback schemes outperform the three benchmarks. Meanwhile, the flops of the transformer-based schemes are much lower than bit-level CSINet, and all the proposed schemes have lower runtime than both the bit-level CSINet and the LSTM schemes. Also, we can observe that the performance of the transformer improves with the model size, providing a trade-off between complexity and performance. We can see that transformer S is sufficient when a few feedback overhead is desired, while the more complex alternatives provide further gains as the feedback overhead increases. In a nutshell, the transformer can better extract these implicit features in the CSI, and fewer feedback bits are needed to reconstruct the CSI at the BS with the same quality, which reduces the feedback overhead and latency. Conventional massive MIMO systems with fully digital architecture require a dedicated RF chain for each antenna, which results in excessive power consumption and extremely high RF hardware costs. The alternative hybrid analog-digital MIMO architecture employs a much lower number of digital RF chains than the number of antennas, where each RF chain is connected to multiple active antennas, and the signal phase on each antenna is controlled via a network of analog phase shifters. The analog phase shifter can be seen as a low-cost passive device, which controls only the phase of the signal. However, HBF optimization is significantly more challenging due to the constant modulus constraint on the analog beamformer. Recently, DL-inspired beamforming has been proposed, whereby prior information is captured from radio channel measurements, such as CNN-based, MLP-based HBF schemes. Herein, we present a transformer-based HBF scheme to obtain more efficient spectral efficiency from limited CSI feedback bits. First, at the downlink data transmission stage, the signal received at the UTH-UE on the KTH subcarrier can be expressed as equation 5. Thus, the signal-to-interference plus noise ratio, SNR, of the UTH-UE on the KTH subcarrier can be expressed as equation 6. Then, the sum rate R in the downlink multi-user transmission can be expressed as equation 7. Our goal is to maximize the sum rate by optimizing the hybrid beamformer. As shown in Figure 10, each transformer encoder implements a part of the HBF optimization. By introducing the structural prior information of traditional optimization methods, combined with the self-attention's feature extraction ability, we can achieve better performance than traditional as well as existing DL-based methods in the literature. Furthermore, we consider two working modes. 1. The first mode requires an estimated CSI matrix as input, which is achieved by the adopted CSI feedback scheme. 2. The second mode relies on implicit CSI as input, which is conveyed by the feedback bits transmitted from the UEs, and in this case, the CSI feedback network is jointly trained with the proposed HBF network. We use the same simulation parameters of channel estimation. And we set the number of UEs to 2. We consider the sum rate as the performance metric. In Figure 11, it can be seen that the transformer-based HBF scheme significantly outperforms SSHP and other DL-based HBF schemes with both complete and limited CSI feedback. Current communication networks do not take into account the meaning or the purpose of the delivered bits, whose interpretation and processing have been left to higher layers. To meet the requirements of 6G wireless networks, however, it is important to propose more efficient information acquisition and delivery methods. The recently growing trend of semantic communication aims at accurately recovering the statistical structure of the underlying source signals and designing the communication system in an end-to-end fashion, similarly to joint source and channel (JSC) coding by taking the source semantics into account. The semantic communication transmitter includes a semantic encoder and a semantic-aware JSC encoder, and the receiver includes a semantic-aware JSC decoder and a semantic decoder. In general, the transmitter can perform semantic encoding on the source according to the knowledge library for obtaining highly compressed abstract semantics, followed by JSC encoder and subsequent baseband signal processing. The receiver follows the reverse steps of the transmitter, where a JSC decoder is followed by a semantic decoder based on some knowledge library. The transformer can extract correlations between different words to form highly abstract semantics. Inspired by this benefit, a DL-enabled semantic communication (DeepSC) scheme was proposed, where a separate semantic coding network is utilized to better extract accurate semantic information. As shown in Figure 12, a transformer encoder is utilized as the semantic encoder and a MLP is used as the JSC encoder. The Rayleigh fading channel is interpreted as an untrainable layer in the model. Correspondingly, the receiver consists of a MLP-based JSC decoder followed by a transformer decoder for text reconstruction. The whole network is trained in an end-to-end fashion to simultaneously minimize the sentence similarity and maximize mutual information. Figure 13 compares the performance of DeepSC in transmitting text over a Rayleigh fading channel with the following benchmarks: Huffman code followed by Reed-Solomon coding and 64 quadrature amplitude modulation, fixed length code, 5-bit, followed by RS coding and 64 QAM, Huffman code followed by turbo coding and 64 QAM, 5-bit code followed by turbo coding and 128 QAM, Brotli code followed by turbo coding and 8 QAM, and the JSC coding approach. The simulation results demonstrate that thanks to the powerful transformer architecture, the sentence similarity performance of DeepSC far outperforms the alternatives based on separate compression followed by channel coding, as well as the JSC coding approach. Hence, we foresee that semantic-aided communication is an important challenge, where the transformer architecture is likely to have an impact on future communication systems by more effectively learning and adapting to the statistics of complex signals, such as text, image, or video. In this section, we discuss several potential directions for future study. Network efficiency and generalization. To successfully apply the transformer architecture to 6G networks, an important research challenge is to optimize their computational efficiency and generalization capabilities by developing effective and efficient transformer architectures targeting wireless applications. Efficient information injection: how to efficiently feed the underlying input, which can include the source signal, CSI tensor, location, traffic and environment information. Input. The transformer architecture is one of the topics to be investigated for wireless applications. Combination with model-driven DL, integrating the transformer architecture into the model-driven framework is a promising approach to further mitigate the performance degradation caused by model inaccuracies. Parallel communication sequential tasks. Transformers are also expected to be successful in communication tasks involving temporal sequences, such as channel prediction and beam tracking. In this article, we have presented the transformer architecture and provided examples to highlight its potential benefits in addressing various challenges for 6G intelligent networks. Considering the applications of transformers from massive MIMO processing to semantic communication, we provided concrete examples to show their competitive performance compared to the other classical as well as recently proposed DL-based models. Potential research directions have also been identified to encourage efforts by the research community to further develop a transformer-based 6G intelligent network paradigm. Thanks for your attention. My report is over. You can browse our research article if you are interested in our work.